I'm Corey Duggan with TLC Engineering Solutions, and I will be your host today for our 6th quarterly forum. I am also the chair of our data analysis and reporting working group that we worked to put together the program for today's forum. So today's forum is really focused around refrigerants. That's a big piece of what the DAR group, or the DARs as we refer to ourselves, have focused on, and the impact that they have on greenhouse gas emissions and overall global warming, and really trying to get our hands around the data and the life cycle, and how big is the impact really there. And so today we've got folks, manufacturers from industry, we've got Chemours, Copeland, Trane, and Daikin to all sort of bring their perspective and planning for the transition to lower and ultra low GWP refrigerants. Our agenda today, we've got hopefully you'll see 15 minutes of welcome. Then we'll move into the forum with some short presentations from each of our presenters, and then go into a prepared question and answer where really hopefully we'll be able to get some interesting conversation going between their different perspectives in the industry about where things are going, what's happening, what's the timing, and then we'll close the meeting out with some updates from our working groups. Quick look at our steering committee for MEP 2040, folks across the industry that you see, probably faces you recognize on this meeting, that really are leading, where we're going in the various groups here. If this is your first MEP 2040 meeting or forum, just a little information about, what we're about and why we're here. You've probably heard of the AIA 2030 commitment, and we have sort of a similar structure where we're asking MEP firms to create a plan for how they can reduce operational embodied carbon across their MEP systems, and really asking for that information, requesting low GWP refrigerants, requesting EPDs for MEP systems, really to try to, encourage manufacturers that that's information that we want, because there's not a lot available. And then to participate in these forums, participate in the working groups and the conversations. And so if this is your first time, you want to become involved, there's information on our website, mep2040.com, I think, or .org. And also you could reach out to any of the members of the steering committee that you see here about how to become involved. Like Andrew said, we now have 70 firms, about 100 plus active members with 38 supporting organizations, and this is our 6th quarterly forum. So really an active group that we're moving forward. And this was kind of new from the last time, but I thought I'd mention it, that to make sure go follow our LinkedIn page for updates about what's going on. All right, so sort of as part of this welcome and intro, I wanted to give a little bit of context for why we're focusing so much on refrigerants, and that being sort of the main focus of this forum. I know, like most folks, refrigerants were part of mechanical equipment that we, it's just part of doing business. And up until really, joining this group and talking about it, that it wasn't like that we had options. It was just whatever the rep provided us, and not really even looking at that as piece of our carbon emissions for the buildings, just maybe looking at operational carbon and then starting to talk about embodied carbon. But that, wanted to point out here that the fugitive refrigerant emissions and their equivalent global warming potential is part of the scope 1 emissions for your buildings. So it's part of that operational phase in scope 1. And, as we've seen and kind of done a little bit of some example studies that I'll show a quick summary of here in a second, that it can be a pretty large impact. And of course, that has to do with, how much leakage there is in a system. And I think, that's part of the data that we're trying to gather, and hopefully that we can talk a little bit about today. This is an example I think Luke brought up in our first quarterly forum, but I think it's an interesting example, that just to look at a typical air-cooled chiller for a 60-year life expectancy over a building, right? And the air-cooled chiller life expectancy is 20 years. So it's going to have to be replaced twice in the lifetime of the building. And, its refrigerant charge and using 410A. And I'm sure that, some of our manufacturer folks will balk at the idea of a 15% emission of refrigerant each year. That's, from an EPA data set. And I think, we're really trying to find good data for that, because it does really drive, what some of this is, and then, how much at end of life. But so over that life of the building, looking at lifetime refrigerant leakage, that it's about 920,000 kilograms of CO2e. And then comparing that to, in a wider perspective, the embodied carbon of a building that, using some, relatively conservative numbers, that it's on the order of potentially 50% of the embodied carbon for a building over its lifetime, which seems pretty crazy, and 11% of the operational there. So certainly has an impact that we need to get our hands around and figure out what we can do to reduce as we reduce other carbon emissions through electrification and renewable energy, and then finding ways to reduce embodied carbon. We're still going to have, that piece left before we can really truly get to zero. And so that's really the inspiration for today's conversation. And, what are our options? Looking at some of the typical refrigerants, R134A in a lot of machines, and then really seeing, down here, some of our newer ultra low GWP refrigerants, 514A, 1233ZDE, 1234ZE, and the stark difference in their GWPs, and, looking for how we can use, and have options like that in the market rather than just the status quo. All right. Pretty close. So now we'll move into our scheduled programming for today. So I'd like to go ahead and introduce each of our presenters. So first off, sort of my co-MC for today, I'm going to hand over for the Q&A is Tristan Coffin. He's the co-founder and president of Effectura. And, they're a sustainability engineering group based in the US and UK. He spent the majority of his time as the director of sustainability for Whole Foods, and has vast experience with high performance buildings, advanced refrigeration, and so on. So I think he brings a really good set of experience to help guide that question and answer later. We have Jennifer Bush from Copeland. Jennifer is involved in the regulatory affairs for more than 20 years and is responsible for managing activities related to policies, regulations, codes, etc. For Copeland around, specifically the refrigerant conversation today. So I think they bring an interesting perspective too. Then from a refrigerant manufacturer standpoint, where are we getting these new options, and what is sort of that life cycle? We have Stephen Spletzer from Chemours. He's responsible for equipment design, testing, technical service, and continues to be part of ASHRAE Standard 15, and so has a wide base of knowledge with refrigerants and their applications to our industry. Steve Kujak with Trane Technologies. He's the director of next generation refrigerants research. Steve's also very active in ASHRAE. He's a ASHRAE refrigerant distinguished lecturer, past chair of ASHRAE 34, and his perspective with his ASHRAE experience, and specifically with Trane Technologies and their approach to the refrigerant transition, be valuable for today. And then finally, Philip Johnston from Daikin Applied, who's the general manager of Environmental Business Development Center. Again, similar perspective to what we have with Steve from Trane, but from another manufacturer perspective there. And he's been supporting purchasing and development activities for chillers, originally as part of McQuay International, and now what is Daikin Applied. So I think we've got a really good group of folks to facilitate this conversation. All right, so first up, we've got some prepared presentation from each of our presenters. And so Jennifer, if you would like to share your screen, and I will stop sharing, then I will turn over the mic to you.
Okay. Let's see if I can move this out of the way. All right, can you see my screen okay?
Perfect.
Okay. Thank you all for having us today. I know all of our presenters could spend way more than 10 minutes on this topic, so forgive me, I'll do my best to cover this in the 10 minutes allotted. Today, I'm just going to focus on the federal regulations that we see, but I do want to note that there are state level regulations when it comes to refrigerants too, just not possible to cover it in 10 minutes. So today we'll focus on EPA, and then maybe we can get into some of that in the question and answer session if needed. But relative to federal regulation, the American Innovation and Manufacturing Act was passed at the very end of 2020, and that gave EPA the authority to regulate HFCs. And within that act, there were really three key provisions around the regulation of HFCs that are important in driving our future product strategies. And so the first is mandating the phase down of HFCs in terms of supply. So this is produced and imported. The second is transitioning the new equipment away from the higher GWP alternatives toward the lower GWP refrigerants. And so this is new equipment limits. And then, sorry, my light always goes off. And then the third is authorizing the EPA to establish refrigerant management standards. So similar to maybe the Section 608 requirements that you've seen before with the HCFCs, and that were around for substitutes for a period of time before the court did vacate those. In addition to these three legs of the stool, I think, as you'll hear EPA call it sometimes, it's important to note that to make this successful, EPA needs to be able to continue to approve new refrigerants for use, new lower GWP refrigerants specifically. And they do this through the Significant New Alternatives Policy, or SNAP, and that authority actually comes out of the Clean Air Act. So this is the program that they've been using for many years, and they continue to use that, which is good. And then also just to note that there is no federal preemption. So as I mentioned, states are able to continue to regulate, and a few of them likely will. If we look at each of the steps, one or three legs of the stool, 1, 2, and 3, in a little more detail, you can see that the phase down prescribed under the AIM Act does align with the Kigali Amendment, with the exception of the very first step, which the Kigali Amendment would have had us step down 10% in 2019, but because the AIM Act was not passed until 2020, our first step actually occurred a few years later in 2022, but the remainder of the steps are aligned. And so on the right side, you can see this table of what EPA has established, or rather the AIM Act established that EPA needs to follow. So annually, EPA does grant allowances to producers and importers, and they are not allowed to exceed the quota that is allocated to them. So producers and importers do have the freedom to continue to produce or import higher GWP refrigerants, but of course that would use more quota per pound than, say, lower GWP refrigerants. So the next big step that we will be taking is in 2024, so 6 months away roughly, we will be decreasing another 30% or a 40% reduction of total relative to that baseline. And if you want more information, I tried to include links below on these presentations, and I assume that these charts would be sent out after the meeting so that you could look into it in more detail if you wanted. The second piece, as I mentioned, was really around new equipment. And so EPA has proposed a technology transition rule. This would establish GWP limits for new equipment. And so on the left, you can see that commercial and industrial refrigeration applications greater than 200 pounds, as well as standalone or self-contained equipment in refrigeration, were initially, the proposal is 150 GWP effective January 1st of 2025. Equipment in the same sector greater than 200 pounds, the commercial and industrial refrigeration would be, or sorry, I said that wrong, greater than 200 pounds. So the larger equipment, 150 GWP, the smaller equipment, less than 200 pounds, up to 300 GWP. And then air conditioning and heat pumps and chillers as well, 700 GWP in 2025. Now, the AIM Act allows any stakeholder to petition EPA relative to GWP limits and timing. It doesn't even have to be in that format, although that's what we've seen. And so the next transition, I assume that as we continue to reduce supply down to that 15% in 2036, we'll probably see some additional petitions come into EPA. And so the timing of another future transition is unknown. But, you know, we don't know where they're going to land. I've just put some numbers out here, purely speculation, no idea where we're going to land. It'll likely depend on what refrigerant alternatives we have, what technologies we have that can use those refrigerant alternatives. You know, when you think of it from a broader perspective, and I'm sure Stephen will get into this, but it's not only the GWP, it's the glide, the capacity, the displacement that you're going to need to make some of these things a reality. And so how does that impact things like footprint or, you know, other things of this equipment that might impact costs? So lots of considerations when we think of future refrigerants, and we're all definitely thinking about it. We all continue to innovate and try to think of, you know, where should we be going? None of us are sitting here around 700 GWP and think that that's the final transition. So just one last note on this slide, the proposed rule did have a disclaimer that the EPA was considering prohibiting the sale, distribution, and export of products containing restricted HFCs a year later. So, you know, in air conditioning and heat pumps, for example, greater than 700 GWP. This was met with a lot of comment back from industry. So we'll see if this holds in the final rule. That final rule is expected by the end of September. I think it's required by October 7th technically, but EPA's goal was to get it out by the end of September. And just a reminder that states may continue to set more aggressive GWP limits. Relative to the third leg of the stool, so this is all around that refrigerant management piece. And really the impact of existing equipment. And so, you know, leak reduction, recovering refrigerant when servicing and turning that back in and making it available to the market as reclaim. All of that is hugely important. And so these graphs just show that refrigeration and air conditioning make up 86% of the global HFC total in terms of usage. So aerosols, foams, and other things, you know, much smaller percentage. And of that quantity that's used in refrigeration and air conditioning markets, over half is used to top off leaks in existing equipment. So this is definitely something that we need to address in order to be able to meet this HFC phase down. EPA is actively working on a refrigerant management rule, and we believe this will roll out sometime late summer. So probably, again, maybe that September timeframe where we'll see that. And then this is my last slide, but in closing, you know, the strategy for a successful HFC phase down has to address both direct and indirect emissions. And so when we talk about direct emissions, you know, we need to use as low as GWP as possible for the equipment that we have access to, consider smaller charge sizes, and, you know, maintain that equipment well. So we have to be able to detect and fix leaks or reduce them or prevent them from ever occurring. If you're not planning to install a new piece of equipment, it's definitely possible to retrofit to a lower GWP refrigerant in already installed base. So do that wherever you can, and of course recover and reclaim refrigerant for use and service. And then when it comes to indirect environmental emissions, you know, energy efficiency continues to be huge because all of the electric that's used to run these systems has to be generated from somewhere. And largely our grids are not 100% renewable across the country. There are pockets of pretty high renewables, but, you know, several that are not. And so energy efficiency continues to be important. And even once the grid is renewable, you know, the less capacity we need, the better. So if energy efficiency will continue to play a key role in strategy as we move forward. I think that's my last slide.
Perfect. Thank you, Jennifer. Stephen?
Okay, let me know when you can see my screen.
I can see it.
All right. So thank you, Corey, and thanks, Jennifer. Great presentation and great setup. Okay, so the first thing I want to talk about is our philosophy when it comes to the design of next generation refrigerants, and that is to always try and find the optimal balance of properties for each end user application. And the important thing to know is there's no one factor that overrules all of the others. Okay, there are many different facets you have to look at. And yes, environmental impact is huge. Sustainability is key. We expect non-ozone depleting refrigerants with low GWP. That said, if you focus just on GWP on one number, you're likely going to miss out on a lot of opportunities because in a number of cases, the lowest GWP refrigerant may not be the most sustainable. You have to look at other factors as well that contribute to sustainability, like performance, your capacity and efficiency. Jennifer touched on this earlier, but for many systems, particularly when you consider these lower GWP refrigerants, the bulk of the emissions from the air conditioning refrigeration systems are the indirect emissions that come from the burning of the fossil fuel, in many cases well over 90%. So when you start getting to lower and lower GWP, you're actually having less and less impact on the overall emissions. So efficiency is key, but you can't look at capacity and efficiency and avoid. Something may look great thermodynamically on paper, but how does it actually play in the field? Can you use existing system architectures or technologies, or do you have to do something very different? Do you have to use a secondary loop? Do you have to use a transcritical system design? Does your equipment need to be a lot bigger, or do you have to completely redesign the compressor? Those are all big considerations. As is safety. Ideally, we want low toxicity refrigerants that are non-flammable, but in many cases, that's not achievable. So then we have to look at how do we minimize the risk associated with flammability, say by using mildly flammable or lower flammability refrigerants like A2Ls. And finally, you also have to consider cost. How much does the new refrigerant cost? What's the investment needed to produce this product? How does it impact equipment design, equipment maintenance, and service? All this has to be considered. Now, with that in mind, these are the refrigerants that are currently on the market or will be coming to the market in force over the next few years. First, we already have safety group A1 HFO blends on the market, products like 448A, 449A, and 513A, which are used in both new equipment designs and as retrofits for older systems, like systems that used R22 or 404A. We expect these products to continue and have a strong presence going forward. However, products like R448A and 449A are likely going to be impacted by the technology transition rule, which is setting GWP limits. They may no longer be able to be used, or likely will no longer be able to be used in new equipment designs once those technology transition dates kick in, and they will now be relegated to the role of a service gas for maintenance of existing systems or for retrofitting. Now, industrial chemicals, products like hydrocarbon, CO2, NH3, they all have their limitations. They've all been around for a long time. They will continue to have a presence. And in some applications, we are seeing growth, or we expect to see growth, particularly, for example, like with hydrocarbons, where they're now allowing higher charge limits under the UL 60335-2-89 standard. Then you have products for low pressure chillers, ultra low GWP products like R1233ZD and 514A that are also very efficient. We expect to see growth with these products. And then a lot of applications on A1 refrigerants today are going to transition largely to A2Ls. You have R410A like A2Ls, such as R32 and R454B. R22 and R404A like products, such as R454A and 454C. And you have R134A like products like R1234YF and R1234ZE. Now, some of these products already have widespread use, like R1234YF in mobile applications or R32 in mini splits around the world. But we expect you're going to see a lot broader adoption of A2Ls going forward. Now, key point to keep in mind, A2Ls today are restricted to new installations or new equipment designs only. However, there is a dynamic underway where certain safety standards, such as ASHRAE 15, are looking at paths to enable the retrofit of A1 systems to products like A2L. So this is a dynamic that we want to keep track of going forward. Now, what happens when many applications transition from A1s to A2Ls? Well, simply put, the most obvious is you're going to see significant GWP reductions in the refrigerants being used in these systems, anywhere on the order from 70 to almost 100% in certain applications. And that's a great boon for the environment in terms of fighting global warming. Now, one of the benefits of A2Ls compared to the incumbent A1 refrigerants they're replacing is they're very, very similar in terms of their properties. This helps minimize design changes and allows for the use of similar system architectures. Now, that said, in some cases, you will see changes where you'll see systems will be smaller overall because of charge limits established with using a lower flammability refrigerant. But another big change is we expect to see reduced emissions overall. First, the A2Ls often have similar to better efficiencies in the products they're replacing, but also as part of the safety mitigation strategy, many A2L systems coming out will have onboard leak detection, which means that you will find leaks sooner, you'll find smaller leaks, and that will help reduce emissions that we have today. Now, designing the refrigerant, designing the equipment, that's only part of the equation. We also have the regulations to consider, which Jennifer did a good job setting up for. I just want to talk about SNAP, one of the requirements for refrigerants. A2Ls are already approved for air conditioning and heat pump applications under SNAP 23, and they're also approved in chillers under SNAP Rule 25. Proposed SNAP Rule 26 came out in May, and this is for refrigeration end uses. And this includes a number of A2Ls in end uses like commercial ice machines, IPR, cold storage, ice rinks, and retail food refrigeration. So we expect this rule to be finalized near the end of the year, and that will open the doors to broader enablement of A2Ls. Finally, I want to touch on codes and standards very, very quickly. These are also updates that are required to enable the use of these products. UL 60335-2-40, the main standard for air conditioning applications. The work in that is largely complete in terms of A2L refrigerants. The fourth edition published in December. They're primarily working on cleanup issues, harmonization with other standards, and a lot of improvements around sensor requirements. UL 60335-2-89, the main standard for commercial refrigeration. The second edition published in December of 2021, enabling A2Ls, but there are a number of upgrades being made to align with what's been improved in UL 2-40. And we expect the third edition to publish near the end of this year or the beginning of next year. For the model codes, the 2024 model code cycle is largely complete for A2L adoption. You have updates in the UMC, you have updates in the I codes, and later this month at the NFPA meeting, we expect updates to be approved for A2Ls in NFPA 1, primarily around warehousing. Now, there's still a lot of work underway on state codes, and we'll touch on this very, very briefly. This is my current map for A2L state code adoption in AC, where by my count, we're just over 40 states that are enabled or near enabled. Enabled means code updates or legislation are both complete and in effect. Near enabled means updates have been improved, but have either not completed the final stages of the approval process or haven't reached their effective date yet. For commercial refrigeration, we're a little bit behind, a little over 30 states approved or enabled or near enabled. And for warehousing, we're further behind still. So we expect those updates to continue over the next few years. And so that's it for me, Corey. I'll turn it back over.
Great, thanks, Stephen. Next up, Steve Kujak. Catch you while we still got you.
Hello, everyone. Hope you can hear me okay. I'm outside, so
Yeah, you sound great.
there's jackhammers going on. So anyway, let's talk about why can't it move to refrigerant selection. So, Stephen referred to this, as it's a balance of various factors. How do I get rid of this window? Various factors. Jennifer all referred to this too. It's, compressors are a component. So refrigerant selection is a balance of safety, efficiency, and the environment. We're going to need better efficiency as we move forward with renewables because we don't have a finite amount of energy we can put on the grid. We're going to be electrifying heating as well. So that's going to be an increased demand and load. And in this transition, unlike the last transition where we were able to adopt safe, non-flammable refrigerants, so the standards and codes that we currently use could just easily allow their use, we've been on a journey for 12, 14 years, understanding the flammable nature of these refrigerants and how to apply them. And I think we've reached the point where we're ready to do that. So it's a balance of the compressor, the heat exchangers, the fluid plays a balance as well, depending on what I can enable for what technologies I can use around the refrigerant. I think of the refrigerant more like copper used in the heat exchanger versus steel, aluminum. What advantages can I use to create a more optimal design? So, whoops, why can't I hide this? No. I don't know if you're seeing the screen that's blocking everything. But anyway, so there's no perfect refrigerant, only the right refrigerant for the right application that gives you the right properties for safety, efficiency, environment. So in the last transition, when I was working as a young engineer, chemist, we did a lot of work around lubricant selection because we didn't have new fluids, new lubricants for the new HFCs. In this transition, it's all about flammability. Can we find solutions that are class 1, ASHRAE class 1, which allow their easy adoption into the marketplace? And when you look at transition right now, there are a lot of refrigerants that are in the transition 5, 10 years ahead of time without regulatory compliance. But the key issue is two things. One, they're non-flammable safety code standards. It's a like for like lower GWP fluids, or like in the case of 1234 a lot of work was done. In the case of hydrocarbons, a lot of work has been done, being contained to low charge equipment where I can balance that safety part while taking advantage of balancing the efficiency of the environment. So when you look at selection of safety, efficient environment, a key part of this in the last 25 years where people talk about, refrigerants have been driving the innovation in the marketplace. It hasn't been the refrigerants driving the innovation in the marketplace. It's been the minimum efficiency standards. So we've been developing newer compressors, newer heat exchangers, new control strategies, understanding, lift and application. And so it's really been around compressor selection with trade-off with heat exchanger design as we get higher and higher in efficiency. Now, in this transition, we're challenged with, depending on the compressor displacement and the application that we need to apply it to, is we're going to have to deal with some flammable refrigerants. Now, what have we found out in the transition earlier in Europe? Non-flammable refrigerants are king when it comes to large charge equipment and how do you apply it. So you look in mechanical equipment rooms, for example, you're going to see in the transition here in a few slides, you're going to have a choice of flammable refrigerants and non-flammable refrigerants as we transition through this phase down program, not a phase out program, through this phase down program. So in the low pressure, large capacity water cooled chillers, you see candidates like 514A and ZD. They've been in the marketplace at the mid 2000 teens. Why? They're non-flammable, high efficiency. Safety, efficiency in the environment, single digit GWPs. As we move forward and to the right, as we get to higher pressure and lower displacement gases, we look at candidates that are more and more flammable. In this case, we look at the hydrocarbons, we look at the 2Ls to deliver the performance we want while trying to balance the safety and the environment as well. So let's take a really close look. Obviously everybody gets these slides, so it's not a big deal. There's two choices in the low pressure area. Why are they in the marketplace? Look, the class 1, right? Non-flammable, non-flame propagating. Efficiency is equivalent to the replacement candidate. Also, the GWPs are single digits. So these refrigerants are, ideal candidates that can be adopted now and move forward with. In fact, they're a large portion of our marketplace, even though there's no regulatory phased out in these categories as of yet. That's mandatory. So as long as you're non-flammable, you can easily adopt refrigerants in the marketplace. Now, the industry's been working really hard on flammable requirements. And as Steven Spletzer mentioned, even looking at now that we've finished this first step, looking at how we could retrofit a non-flammable high GWP fluid with something like a 2L flammable refrigerant as well. So the industry is innovating constantly and looking at balancing safety, efficiency, and the environment, right? Now, in the medium pressure area, we have a bunch of different choices. The two HFOs are on the right, single digit GWPs, 2L flammable. There's going to be offerings of non-flammable, little higher GWP fluids, 513A, 515B, depending on the requirements. So you're going to have more choices, what I call more fragmentation in the marketplace. So for example, what we're finding out from customers is to use a 2L in an existing equipment room in the United States, it's most replacement market. There's a lot of water cooled market in the United States. Instituting higher ventilation rates in the equipment room is maybe impossible, but also very expensive. So it's not so much I have to increase the ventilation rate sometimes between 2 to 4 times. It's actually where I find that makeup air to allow the ventilation to occur, which has been the challenge for designers. So this balance of safety is a huge challenge in the industry and along its adoption. So adoption of 513A and 515B is going really well because it's non-flammable. Flammable refrigerants require more cost for consumers and customers. So we look at the largest space in the United States for air conditioning. It's the 410A space. So the EPA, about 40% of all greenhouse gas emissions come from 410A in the products. And that's a combination of how much it's used and leak rate in that range. Some people are still using R22 on their rooftops. So in this case, we have two solutions that are entering the marketplace around the world. It's 454B and R32. R32 I first tested in 1993. It's half of 410A, right? We put 125 in 410A to make it a class 1 so we could easily transition. I have to do all this work we did. 454B is just a blend of R32 with YF to optimize its properties and different characteristics, much like what Steven had said earlier. It's like, how do you balance that safety, efficiency, and the environment? In this case, we can get the lower GWP, make it look a lot like 410A. We're constantly doing this balance of this act. Now, you see the higher GWPs here in this category. You also see higher GWPs in the non-flammable medium pressure. Those are going to be what I call interim replacements. We're going to have to get lower at some point, like Jennifer said, but that technology has a lot of trade-offs today. Tomorrow, there's a lot of innovation going on that can actually help us transition likely if those fluids get developed and how we might apply them. But maybe the applications have to change too, right? We're going to go more to chilled water or direct expansion. We're going to need more heating, electrification of heating. How are we going to handle that transition? So, that in the end, there's no perfect refrigerant. It's just the right refrigerant for the right application, applying the technology, the compressor, heat exchangers, components, and the refrigerant with the right balance, safety, efficiency, and the environment. And whatever gives the lowest life cycle time performance, as well as less complexity, less cost, to make that transition. I always think, non-flammable refrigerants are cheaper than brains because the 2L requirements, the industry invested a ton of money trying to figure this out, and we've done a great job, and we continue to work that stone quite a bit. But in the end, continued leak tightness is a key no matter the GWP. I got that question today when I was doing the talk. GWP1, Steve, why are you worried about leaks? Leaks are important because anything that gets in the environment is always a source of pollution in some manner. Plus, the refrigerant has a lot of value as we move forward because of the allocation model. People in the industry has been working over the last 25 years since I've been in it to continue to improve leak tightness. So that's it. Thank you.
Excellent. Thanks, Steve. All right, and our last presentation before we get to the question and answer, Philip.
All right, can you hear me okay and see the screen?
Looks good.
All right, so I'm going to cover this agenda, Daikin approach to refrigerants and impact on performance. And yes, we've got a fancy Daikin graphic there about driving to reduce greenhouse gas emissions to net zero. And then this is a very busy slide, but if you think about it, if you look at the bottom right in the graphic, it covers all the same things that the previous presenters were covering. And it settles down to, you know, the four majors, which is safety, you know, energy efficiency, environmental impact. Now, I will say for our businesses that manufacture equipment, whether it's refrigeration or HVAC, and me in the applied world, you know, there's no big corporate ogre saying thou shalt use this refrigerant. We basically have the ability to select whatever is the best balanced refrigerant for each application, but it's to mitigate total environmental impact. So that's our big focus, is total environmental impact. And if you want, you can find these links to, in the bottom right, to what is Daikin's refrigerant policy, and also some of the environmental statements that we've made on climate change. Now, looking on the bottom left with the black text, these are some of the steps that, or things that went through our mind when we were approaching what refrigerants were we going to use in the Daikin applied world. And clearly we wanted to avoid ODP substances. We're not into higher toxicity B substances for what we're doing, but again, this is a spot in time, and maybe someday we will have to use higher toxicity B substances in some of our systems at some point in the future. And of course, we didn't want to use higher flammability class 2 and 3. Obviously, you heard from both primarily Steve, the two Steves, was we need to be able to use existing system architecture to move quickly, and you needed to meet that UL safety requirement as well as ASHRAE standard 15. And then there's a last thing that really wasn't said, is you need to be able to find it. It needs to be available. So you need to be able to buy it and purchase it in the country in which you're manufacturing the equipment. And that's primarily because both the Kigali Amendment and the AIM Act look at bulk production of chemicals by the major chemical producers and then some importers. So you need to be able to get it, and that's a big factor. So when you start looking at this particular slide, the reason I like to show it is really to say A2L refrigerants have been used all around the world for the better part of a decade. And in fact, there's certain countries that are part of the developing system that are almost using it exclusively in their residential equipment. So India, for example, I read somewhere recently 90% of their residential equipment is using R32 within their mini splits. So there's some 200 million units in operation all around the world using A2Ls. So I wouldn't necessarily worry about that. And they've all tended to settle on R32 in other parts of the world. Now, I also like to show this slide, and if you were to normalize it, it's basically a theoretical model. It was third-party paper looking at efficiency or COP relative to 410A in this particular chart on the vertical axis, and then capacity on the right-hand axis. And they only looked at single component refrigerants, yet what you're going to start to see is a lot of blends. And clearly R32 is the only one that they said will work in the high pressure systems to replace 410A as a single component that yields both improvements in capacity and efficiency as a single component refrigerant. And then you see YF down here, down in this bottom section, clearly it was targeting 134A, which is why you see it in automotive. Now the cool thing, like Steve and the two Steves mentioned, is when you plot some of that YF into it, certainly it will dilute some of the performance of R32, but it was targeted to perform just like 410A. Okay, so you're going to see both in the market out there being used, and they're both going to perform equal to or better than 410A. When you looked at we looked at some tests, and in the Daikin applied world, we said environmental impact's critical. And in the applied world, what we prefer to be selling is anything with inverters or VFDs, whether it's a big chiller, big centrifugal, or whether it's our Rebel and Rebel applied systems. And certainly we do have fixed speed compression, because some of the products that we offer, people are only willing to pay standard efficiency for that. But our bread and butter is on variable speed capacity. And why do we like that? Life cycle climate performance, as well as life cycle operating costs, are a really good position for us when you're not for the sort of customers that we tend to deal with. So what we did is we took a standard inverter rooftop unit that we've been making for 15 years. In its particular design, it was 410A, and we swapped out the refrigerant, and we normalized this performance. And we got about a 10% efficiency improvement when we moved to R32. Yet none of the models or theoretical assessments say you should get that level of efficiency improvement. And certainly you're not going to see it in fixed speed equipment. But the primary reason with the inverter equipment is because we got that 8 to 10% more capacity that Steve Kujak mentioned with R32. So what ends up happening? Your compressors, the inverters, start turning a lot more slowly. You draw a lot less watts. So we picked up a huge amount of efficiency to deliver that nominal capacity of that unit. And then similarly, we used 454B, and because there was, like Steve said, a 3% capacity loss, that compressor had to run harder. And therefore we lost a little bit of efficiency. So again, this is kind of what you see in certain inverter type units, but you're not always going to see this in fixed speed compression, because frankly, you can go to compressor manufacturers, which includes Daikin, Copeland, Danfoss, and others, and they can come up with 454B compression that will be equal to or similar performance to 410A. Okay. And that led to, this is what we really believe, and I heard it in Jennifer's Prezo as well as others. We really care about life cycle climate performance, which looks at both the direct effect and the indirect effect from the energy use. In a nutshell, here in the United States, at least, the vast majority of our electricity still comes from the burning of fossil fuels. So the indirect effect is 80 to 85% of this equation. So we cannot sacrifice efficiency in the development of our equipment. In fact, we want to optimize it wherever possible. And if you were to build globally on that theme, there's been data published that suggests air conditioning usage is going to go from about up by a factor of more than double. I think it's 150% over the next couple of decades around the world, which means there's a lot more refrigerant, a lot more electricity being used. And when you're doing that scenario, that's what goes into the models that are feeding Kigali Amendment and the Montreal Protocol and the IPCC looks at. So we got to focus on super energy efficient systems, as well as driving down the GWP of our refrigerants, simultaneously. So that in turn led to, well, how does it compare really in terms of a model? In this particular model, it was a residential model, so it wasn't my bread and butter on the applied side. We hired a university to look at what is the estimated LCCP for both air conditioning, heat pumps, and CO2 equivalent emissions across the USA. So it was all the USA, all the bin models, everything rolled in. The first thing you see is here's the example of the indirect effect from electricity consumption is this dark blue bar. It's the single largest piece, whereas the direct from leaks are your dark orange and your light blue gray kind of up top. And so let's just say your efficiency gets worse at some point in time. Well, it wouldn't take much for that dark blue box to get bigger. Now, the cool thing moving to this low GWP refrigerant, if you can pick up just a few percent of efficiency, not only can you lower the direct emissions, which is your gray and your orange getting much smaller, but you could also improve your dark blue bar by a few percentage points over the life cycle of the equipment. And I think you would see this for both 454B as well as R32. And that's moving in the right direction for the planet. Moving on to medium pressure refrigerants, and I cannot see everything on my screen just due to the Zoom taskbars flopping over. But if I could point to 513A, a lot of people wonder, because we are offering 513A as a replacement 134A in pretty much every screw centrifugal chiller that we manufacture. And you wonder why, right? Because you lose some efficiency. 3 to 5% worse efficiency. Its GWP is okay. It meets the 700 GWP limit set by the EPA and the 750 set by California. But no, this is not a long-term refrigerant. This is a mid-term refrigerant. This is a short-term fix because it performs a lot like 134A, uses a lot of the same materials, and only minor changes were required to certain materials within the equipment and in the controls. So it was a quick to market solution simply because there are 12 states that have a transition date of 1/1/24 for those chillers. But in turn, you look at the second bar over here, there's that 1234 ZE that was mentioned. And sure enough, you see a big drop in capacity versus 134A at 25%, but you see a bump in efficiency in this particular model from the AHRI research report. So that's moving in the right direction for efficiency using 1234 ZE and A2L. So if we want to talk about that a little bit more, 1234 ZE is definitely part of long-term plans for anyone who's using 134A. Again, you got to offset that capacity drop by doing some pretty significant redesign work in your compression side of your chillers. And it is a group A2L. And as Steve pointed out, when you start moving to flammable refrigerants, even in machinery rooms, the new standards, whether it's 15 or 2-40, have some requirements. So it may not be an ideal replacement. You may not want to upgrade your ventilation, for example. So chemical producers came up with an idea that they blended in a higher GWP refrigerant called 227EA in a very small amount, 8.9%. So it performs pretty much the same as 1234 ZE. The GWP bumps up to 292, but all of a sudden it passes the test to become a group A1. So that's some of the innovation that you're going to see, and we're going to have to continually be looking at blends at some point in the future. Okay. 514A, Steve mentioned this, and he'll be the expert because there is one OEM offering, and it happens to be where Steve Kujak comes from. It's a blend of a couple of very low GWP refrigerants, ultra low GWP. It's certainly a low pressure refrigerant. And it is a higher toxicity B, just like 123. The other alternative Steve mentioned is 1233 ZD. It's being offered by all majors. I don't know if it's across all their product lines. It certainly isn't for us yet because the development is quite exhaustive and takes a lot of time. It is a single component, has a GWP of 1. It just happens to be a group A1, the no flame propagation and lower toxicity. Other than that, this is just a summary, and I'd rather open it up for questions. It summarizes the sort of things that I've said here. And if you have any questions, I guess we're all here for you. That's it.
Great. Thanks so much there, Philip, and all the presenters. So at this point, I'm gonna, turn it over to Tristan to start our question and answer. I know we've got some, prepared questions. I don't know, Philip, you may want to stop sharing your screen. I think.
Oh, I'm sorry, I thought I was. Stop sharing. Thank you.
There we go.
Yeah,
So
you
we
bet.
see everybody's faces here. So Tristan,
Yeah,
you want to take it?
absolutely. Well, thank you to everyone, all the presenters, and thanks for everyone who's put a number of questions in the chat already. As Corey just mentioned, we do have a number of prepared questions that the forum pulled together, and there is a lot to unpack here. As everyone's probably gathered, this is a very hot topic. There's a number of participants, so we'll try to get to everyone's questions, and we'll try to make this a fruitful conversation. Fortunately, we know Steve does have to jump in about 10 minutes, so might start with pointing some questions directly at him. Yeah, and I just want to call out that this is a really important conversation. Corey helped lay some of the groundwork, but to maybe lay it a little bit further, refrigerants themselves have been identified as a 0.5 degrees Celsius warming opportunity to avoid by the end of the century. So, and that again is the refrigerants solely. That has nothing to do with the other efficiency components and other environmental impacts that we're going to try to discuss in a little bit more detail here today. So before we leave Steve lose Steve, excuse me, I think want to maybe start with a question around 454B versus R32 as it relates to performance in 410A machines or equivalent machines. And Steve, want to get your perspective on that before you have to head out. I think you might have some questions or ideas on that subject.
Well, in HVAC designs, we designed a minimum efficiency standards. So, you know, Philip showed better performance when dropping in. I put 32 in a 410A device. I have worse performance because you optimize around compressor displacement, pressure drop, mass flow rate, and things like that. And so it's a matter of taking cost out if you have a higher efficiency fluid. So the thermodynamics of 454B and R32, you saw my presentation, are very close to each other. So, you know, thermodynamically, they're both good fluids. It depends on the GWP, right? I mean, if you can play the games of, you know, what's your leak rate and this and that, but in the end, efficiency is controlled by minimum efficiency standards, and that's driven all the innovation in our marketplace. The refrigerants are a direct emission. It's just GWP based, allocation based stuff. And so, you know, you could choose either one. They both meet the 700 limit. People are going to use both. I don't think there's any advantage or disadvantage. I'm looking past them because we need to be below 300. This makes this transition easy and orderly outside the 2L requirement, right? So I'm looking for, how do I get to less than 10, right? I mean, that is the goal. Let's be less than 150, less than 10, less than 300, whatever it is. I need to get there and be prepared for that, for basically taking the refrigerant emissions out of the equation, right? Completely. So I can focus on compressor technology, heat exchange technology. You know, Tristan, we're going to be using a lot more refrigerant potentially when we do electrification of heating. And we're doing some reversal heat pumps, yada, yada, yada. But by far, once we electrify, we're going to use more refrigerant. We may have separate devices. Now, we're going to save a lot of emissions on the carbon emissions, not burning fossil fuels, and get better efficiency on the heat pumps. But we really need to focus on, you know, kind of 4 pillars, right? Refrigerant management we're talking about here. There's efficiency, right? There's electrification of heating. And then we have to figure out how to balance all that with renewables and the grid, right? At the same time. So here I am talking about refrigerants, and I'm not talking about refrigerants. I'm talking about, you know, how we balance things that really are going to be the macro drivers and drive all the innovation in the marketplace.
Yeah, it's a huge subject matter in terms of the balancing, and some folks are putting some notes in here too. And it's not just about even electrification. I think from electrification alone, the last stat that I saw was that about 300 million heat pumps are going to enter the market by the end of the decade, and I'm sure that number is increasing.
Well, it'll be 2,299,000, whatever it is. I put one in, so
yeah, there you go. So you're
one down.
You're either a part of the solution or part of the problem, right? Depending on how you're looking at it. So no,
one down.
I love it.
You can mark me down one.
There you go. There you go.
You got rid of that old R22 machine, Steve?
Yes, I did. Yes, I did. I used 410A though. I didn't wait.
There you go. There you go. Well,
like carbon emissions are much more reduced by 50%.
And that's a really important piece, letting perfect be the enemy of the good here. And I think that's a lot of what we want to try to chat through. And Steve, again, before we lose you, you mentioned that you tested R32 in 1993, and everyone that's presented today talked a lot about the scheduled phase down of the current refrigerants in use and what the replacements are going to look like. And obviously MEP 2040 is really focused on options sooner, and being able to not even necessarily go to the quote unquote, I'll call them interim solutions that we're focused on right now, the moderate GWPs. But Steve, to your point, getting below 300 or even below 10. And I think that the main question that the group has is they want options now and really ahead of the government required scheduled phase down, and even ahead of the technology transition, which you know, the rulemaking is obviously proposed. It's set to be finalized, I believe, in October of this year. So we'll have a little bit of a better understanding of where the market's headed at that point in time, of course. But if I were to put the question maybe directly at you, Steve, to start, and then open it up to the group, is when can all the folks on the line today, as designers, as end users, and the like, when can they start purchasing this equipment with alternative refrigerants? And I know it's application specific, so maybe if you went from chillers to package units to multi-splits, to give an idea from your perspective and maybe from Trane's perspective on when they're going to be able to start purchasing the next generation of all refrigerants.
Yeah, so you kind of have 2 questions there. So
yeah, sorry. There's a lot. There's probably a ton of questions within the questions, so feel free to answer them, and I'll circle back. Yeah.
Unpack all that. So
yeah.
Refrigerants are in the marketplace where non-flammability or safety can be ensured, which is either small charge equipment, right, like for hydrocarbons. And so you see those as early as 2015. Some of these refrigerants have been in the marketplace, right? For example, 452A, which is not regulated in transport refrigeration, was introduced in the marketplace in 2013 in Europe. Why? non-flammable, easy to adopt. Now the industry has been running with scissors, right? I say, so you see this, why aren't you putting new stuff in? Well, the standards have to get in place. We've been doing all the work. You have to get the building codes up. Oh, by the way, if we had all those in place 4 years ago, you'd see them right now, but we just can't implement them regulatory wise, right? So once we have that in place, you're going to see, I think my personal opinion is you're going to see lower GWP options coming after that, because now the 2Ls are out of the way, right? We have the building codes, people are going to get comfortable with them. So this is going to enable us on the next transition, right? And help us move forward quicker. We just didn't have the ability to go, how do I give a building designer, how do I design a product to handle all the flammable? I gotta need sensors. I gotta develop sensor technology, right? I gotta understand 15 to be updated in the building code. So I mean, to me, you know, we're running kind of with scissors in that area. That's why you haven't seen it. Now, you see these ultra low GWPs in various other applications. Get back to your first question. You see carbon dioxide in the stationary refrigeration. The question is, you have to tell us why. There are no minimum efficiency standards in that product category. So, how much better can you get? Can you measure yourself? Hydrocarbons have been introduced. Why can you do that? Small charge equipment is inherently safe with a highly flammable refrigerant. You see refrigerators, you see, you know, the industry is up the charge size to enable more stuff, but, you know, there's corners and pockets depending on the balance of safety, efficiency, and the environment, right? If you have no efficiency standards, you can do what the hell. I mean, people ask me every day, why don't you design a CO2 air conditioning system? Well, if it was 1980, I could give you it. Today, with the SEER ratings and the IPLV stuff, can't get there from here thermodynamically or hardware-wise. I can't throw enough at it to get all the heat balance back where I want. So it's a balance, that safety, efficiency environment. Get back to that, right? It's just, with those efficiency standards, they're preventing, I shouldn't say they're preventing, I should say they're enabling higher efficiency products, and other refrigerants, you know, copper and other, you know, all components are going away because you have to have new technologies. Like maglev allows a point or two of efficiency in the compressor, right? Drag gets away. So I mean, it's all this, you know, I'm polishing that rock on the efficiency side, right? The refrigerant's part of it. It can be a big stepping stone, but it's not the whole stone. Right?
Yep, no, that's huge. Philip, do you want to add anything there?
Yeah, I won't. Okay, so globally, things are moving at a different pace. That's clear, due to different reasons. I will say here in the United States, one of the key questions is when will you be offering low GWP refrigerants? In the vast majority of Daikin chillers, we're already offering them. They're out there. I would say it's a little more slow when it comes to the scroll chillers, R32, but they're going to be out imminently in our selection software for our reps to be doing it like this month. And I think that's the same for the other three major chiller manufacturers, that they're offering their low GWP solutions across the board in centrifugal and screw chillers, as well as scroll chillers using both R32 and 454B. Because Carrier is going with R32 in their chillers, but 454B in their ducted systems, you know, their ducted DX. And I think JCI and Trane have announced 454B in their scroll chillers. And I think they're out there promoting that. When it comes to everything else, it comes down to getting those codes updated, and it's really, really close. We have so many people, whether they're industry folks or even actual companies, like we have a person out chasing getting codes changed locally in every state. And sometimes it has to be local because it's done on a county by county basis. An awful lot of states don't have statewide building codes. So that's really, really critical. Then you have development timelines that are pushing right up against the deadlines, which for DX equipment is January 1, 2025 across all the USA. There's no deadline at all in Canada. We do a lot of business up there as well. And then for VRF equipment, the deadline is 1/1/26 because they got an extension because of the probably added complexities of getting those systems redesigned. But as products come available, they're going to be launching. So I'd start looking for them the latter half of this year throughout and into 2025 for all the DX type systems. That aside, hey, you can go into your local Home Depot and you'll see window air conditioners already using low GWP refrigerants. Take a look at the data plate. Again, low charge, like Steve said. I don't think I want to get into talking about what Daikin's global plans are for our next round of refrigerants, because one, it's kind of secret unless it's published overseas. I will say that publicly, yes, Daikin has used R32 for a long time in Europe in mini splits, and also in a product they have there that we don't offer in the States, which is making hot water for in-floor heating as well as radiators and such. And they're also looking at, and they've announced that they're going to be using propane as a refrigerant, as well as 454C in very small models, because again, that's almost like a mini chiller that makes hot water. It sits outside the house. You have less worries with codes. You know, when you have an air-cooled scroll chiller, essentially the safety standards are silent. They're mute on what refrigerants you can use in a chiller that's in an indirect system. The key question then becomes, can we develop a product that we're comfortable with? And can we develop a product that engineers like yourselves and contractors and owners really want to sell and use? Okay. So I would say expect a diversity of refrigerants going forward. It's going to be very difficult. I mean, I've already said, when you switch to 410A, you're going to see R32 and 454B. Whether it's a mixed bag for the four majors and chillers, kind of 50-50 using the two. It's pretty clear that most US companies in their traditional ducted equipment are going with 454B. Daikin may be a bit of an outlier because we're focused on primarily Daikin applied and, you know, doing ducted systems with super energy efficiency with our inverter driven systems. And then when you look at non-ducted systems that are primarily engineered and developed overseas, but also some of them are manufactured here, most of them are all using R32 globally. I think it's highly unlikely they'll switch to something else, but they might. So right now you're looking at, you got two options. Well, what's going to happen in 2027, 2028, 2029? Folks like yourselves are asking us to move more quickly. We're going to start looking at other options, and it may come out. So it may not be two different refrigerants in the high pressure refrigerant world. You know, we might have to start looking at different refrigerants, just like what they're doing in Europe. You know, I can use this refrigerant in this application, or I can use this refrigerant in this application. And we might have to start looking at blends with more than two refrigerants, which bring their own complexities. We might be looking at more proprietary HFOs blended with some of the non-proprietary refrigerants. It might even be certain natural refrigerants like the propanes, ammonias, or CO2s of the world in very specific applications. But it's going to be, certainly there's risk for all of us, and we need to study it and work hard and work smart. But I think we're going to start seeing more innovation and more diversity in our refrigerant.
That's really helpful. And you kind of answered my next question, but you also kind of pled the fifth on what was coming as the next generation beyond the interim step that we're looking at now. And I think a lot of folks, yourself, Steve, and others, but I'll open this up to the wider panel here, is have talked about performance, obviously energy efficiency, codes and standards being some of the challenges to get to what I'll call a best option versus perhaps the less bad option, i.e. a moderate GWP versus an ultra low GWP in some of the applications that we're talking about. But perhaps just to underline it, is performance, energy efficiency, and cost in your minds the main, and for that matter, safety, the main prohibiting factors right now to go to call it an ultra low GWP solution across all applications? And I open that up to the group.
So who do you want to start with?
Well, you spoke up, so you just volunteered yourself. How about that?
Okay. I mean, so we talked about this a lot already. There's no one factor. There's a whole host of factors. And just for example, now going from A1 to A2Ls, there's a whole host of issues you need to consider. Okay. And we're getting ready, we're ready on a lot of them, and we're going to be ready on others in the very, very near future, but it's taken a long time. It really has. It's been a major effort. So we talked about 513A earlier. Okay. Why are people going with that when its GWP is over 600? Well, that was, like I said, it was an easy hit where same application, you can reduce your GWP by 56%, minimal changes. Going to an A2L opens up that can of worms that you have to deal with. So yeah, that's a big factor. It's cost, ventilation, safety, all these things come into play. And again, it's very different for every application, but yeah, we've all hit on it already. There's, several different considerations for each product and each application that you need to look at.
That's helpful. Well, given that and the limitations of some of the next gen refrigerants that we're talking about, but also the growing environmental concerns associated with refrigerant emissions, do you believe there needs to be a paradigm shift in terms of alternative designs that could better enable, let's call it, the less bad solutions? So in other words, I've said this on many occasions here recently, the US has an addiction to low cost, high efficiency packaged rooftop units, right? And those are probably, at least in my opinion, and I think there's a lot of what we're hearing today, that's one of the biggest challenge areas in terms of transitioning to a ultra low GWP solution, for example. You think that we need to start thinking about designing out some of those solutions and start thinking about chiller systems where today we can get to lower GWP? And I know that's very specific to new buildings because it's very hard to retrofit in, obviously, in existing buildings. And then questions have come up around VRF as well, and the types of refrigerants that have been being used in them. And obviously with VRF, you're using a whole heck of a lot more refrigerant because you're piping it throughout the building. Again, there's a place for VRF, especially in existing buildings, historic buildings, et cetera, especially as cooling becomes more necessary. But I guess maybe to put a point on my question, do you believe there needs to be a paradigm shift in terms of the applications that we're designing into specifically new buildings to allow for the best solutions versus just potentially better or less bad solutions? Don't all speak up at once.
It's a very difficult question to answer. There is no yes or no answer, except to say that if you're a consulting engineer and you're working with your owner has to define what it is that matters to them. And if it first cost, then you're probably not going to be coming to me for inverter compressor heat pump rooftop units, right? Or inverter compression VRF systems. You're going to be looking at a rooftop unit or some minimum efficiency stuff where at least my company Daikin Applied doesn't play. And I think it comes down to what does the owner want balanced with, you look at regulatory requirements, and then what are you capable of doing? What are you capable of finding? So certainly there will be tailwinds caused by the environment for certain building types and system types. And then there will be headwinds to certain system types based on that for certain system types. I don't think it's up to us to say black and white what that choice is. If we could come up with a circular economy with our equipment, including refrigerants, which we are attempting to do in certain parts of the world and studying it and seeing, can we own the refrigerant? Can we take ownership of that refrigerant? Can we ensure zero leaks or close to near zero leaks? Which if we're not having leaks, we don't have this problem. And then in turn, you could definitely take ownership of that refrigerant, reuse it with your existing ownership of that equipment, or perhaps reclaim it. So there are opportunities, but they're also complex and they're so different compared to what we're doing today that I think it's going to take a lot of brain power, and a lot of you on this call are part of that solution because you are our customers. So we do have to listen to you and we need to figure that out. It's about the best I can say, Tristan.
No, it's a great answer. I appreciate that. And I do want to come on to leakage and life cycle refrigerant management. I think it's a really important subject that we do need to cover. And but I do have a few other questions on some of the points that have already been made. And Stephen, specifically, you referred to the industrial chemicals. I've commonly referred to, and I think a lot of folks on the call will probably refer to them as natural refrigerants or nature identical refrigerants, IVs, those things that are naturally occurring, CO2, hydrocarbons, ammonia, as you pointed them out. Curious in, why we're seeing more traction in places like Europe than we are here in the US, using CO2 and propane in particular for AC heat pump applications, and why we don't see the OEMs leveraging the experience in Europe given there are obviously most companies are global, the OEM specifically, why we're not seeing that opportunity be leveraged across the pond, so to say, and from other parts of the world. And I think I can't recall who mentioned it, but even R32, for example, being used in Asia for decades now. Why aren't we seeing leverage across different parts of the world, but specifically in this case for natural refrigerants?
Okay, so first thing is multiple parts to that question. So first thing to keep in mind, and Europe has been ahead of us in terms of their regulations and schedule for a while. For example, as an example, they phased out R22 equipment 10 years sooner than us. Okay, they had their F-gas regulation in place and they were implementing things before we had the AIM Act. So there's a timing difference, first of all. And then as far as you heard Steve Kujak mention earlier, for these large CO2 systems, where's the efficiency standard? Well, if there's not one, then is efficiency your chief concern? I would say that manufacturers in the US have leveraged the learnings from Europe and other parts of the world, the good and the bad. Okay. There are climate differences between here and Europe, for example. Okay. And CO2 has been studied, it's been looked at, and it is growing here. Do I think you're going to see CO2 here in the US the way you are in Europe? I don't. Others may disagree. The inherent inefficiencies of that product and the inherent limitations that we talked about for the, if you call them natural refrigerants or I call industrial chemicals, those limitations have been there from the beginning and they haven't changed. All we found is we found new technology to help combat those limitations. Okay, so a lot of those technologies come over here. We find ways to make equipment with hydrocarbons use less charge. We find different ways to make the systems more efficient, variable speed compression, ejector technology for CO2. So it's a mixed bag. Okay, we're taking the good and trying to learn from the bad.
I appreciate that answer. And I know Jennifer's focused more on the phase down side of things, and I don't want to put her on the spot, given I know that's more of her focus and conversation. But Copeland, for example, has CO2 compression technology. It's being used in a variety of applications, both in the United States as well as, of course, in Europe. And maybe, Philip, this is a question for both you and Jennifer, is do you believe that there's opportunity to leverage some of those technologies more than we're leveraging them today? And Stephen, you said it. I mean, I think there's definitely challenges, and we're starting to overcome those challenges with technology. And I'm glad that you called that out, because on its own, if you're rowing back to 3 decades ago, without those technologies, the efficiency, the cost, et cetera, would be overwhelming, right? But I guess to Philip and Jennifer, do you believe that we can do a better job at leveraging natural refrigerant technologies today for deployment in AC heat pump applications?
I'll defer to Jennifer.
Okay. I'll just build on what Stephen said. I think some of the applications that we see in Europe are different, right? So if we have hydronic heating, CO2 is a really good solution, et cetera. Now, what I will say, in commercial refrigeration, obviously CO2 is a different animal. And we have lots of CO2 products around commercial refrigeration today. We have more evolving in that space. But, we continue to innovate. We haven't given up hope for CO2. And is there ability to leverage what we've learned overseas? Absolutely. But we have to keep in mind that balance relative to the architectures we have here, especially in existing buildings. I think new construction is different, but existing buildings, our architectures are just different than what we have in other regions. So largely that built environment looks and feels different. But, Copeland has 14 different DOE funded projects right now around research and innovation, largely with our OEM partners. So in collaboration there. And so we do continue to innovate around multiple lower GWP fluids, including what you would call the naturals. So we haven't given up hope. I think in order to make that a reality, we have to continue to evolve our safety standards, both in terms of product safety standards, application safety standards, and then we'll need EPA approvals for these additional lower GWP refrigerants as they become available. And even from a synthetic standpoint. I don't know that we have the full deck of cards yet. I feel like there's still opportunity to innovate there as well. So we're not closing any doors at this point. We are open and continue to innovate and build those technologies that we can then leverage, whether it's CO2 or propane or ammonia or some other fluid.
Very helpful. And maybe that's a good follow-up question. You've kind of alluded to it, and I know some may not want to answer this because you can't answer it because it's maybe not be publicly stated yet, but maybe just put it point blank, or are your organizations, and you just talked about working on CO2 and propane applications, but are you working on other 10 or less GWP solutions today? And what do you think the timeline is for the deployment of those in the market? Is it 10 years? Is it 20 years? What is your kind of timeline? And I know, Philip, you said you couldn't speak to that directly, but
I think I can answer some of that because clearly I've said in very specific applications, Daikin has already publicly announced that they're working on CO2 and propane. So, propane in these small residential hot water producing systems, for the European market. And frankly, I could see that coming to America if people want to heat with hot water. I think and then CO2, they're studying that even in VRV overseas. And I think there are some very serious challenges in that strategy. I will say too, we have a global R&D actually a few different global R&D organizations, depending on the products or systems that are being focused on. And I don't think that's any different than JCI Trane or Carrier. And certainly Copeland, when we chat with Copeland about their compression technology, they are referencing their global R&D centers that are all around the world. The tough part is, in India, I showed that they're all using R32 or 90% of the residential equipment's R32. And they didn't move because they were told to regulatory wise. They didn't have, they're ready with the safety standards and they're ready with the product, and they felt that those products had better value. And in that particular, the value statement has to do with the fact that R32 happens to be cheaper than 410A, at least it was. I haven't checked recently. And also they were able to reduce charge by 30 to 40% in those mini splits and be able to provide better efficiency. So it was a no-brainer, people want to buy it. And I think some of that can happen in the equipment that we're doing here too. But when you start looking at the alternatives that follow, it's a more difficult value proposition. So I suspect it'll be driven more by what is the true regulatory demand that is forcing action, because it will force us into certain system types or solutions that either drive cost up or reduce efficiency, or maybe we have to drive costs up to hold efficiency. And then you have to manage certain things like glide in certain applications. So that is a pretty big adjustment in how you engineer your equipment, how you design your equipment. So to me, it's just going to take a while. And like Jennifer said, I think all doors are open in our advanced R&D organizations for what's going to happen.
Appreciate that. I know we have to give a bit of time for the forum's kind of logistical items towards the end here. Corey, are we doing okay? We have a few more.
Yeah, I think we can probably go another 10 minutes.
Okay, fantastic. Because I know there's a
what
lot
I'm
of questions
deciding, at
that popped
least.
up as well. So, all right. Well, not to add another kind of complication to the discussion, but I think all of you at some point or another in the conversation have mentioned that balancing properties for refrigerants is incredibly important. And Philip, you referred to life cycle climate performance. And like I said, hate to throw another curveball at the group here, but how are you all considering PFAS as a growing concern as part of the alternative refrigerant equation, given the European Union, for example, has already started to look to regulate PFAS, which puts a lot of these alternative refrigerants that we're talking about on the chopping block, with perhaps the exception of R32, which may be one of the only exceptions at this point in time. Do you see it as a growing factor in how we look at alternative refrigerants into the future? And Stephen, why don't I start with you on that one?
Sure. Okay. So obviously we're looking at the PFAS issue, okay, but it really begs a bigger question, and that is, what is a PFAS? Okay, and the answer to that varies a lot depending on where you are in the world. By some of the definitions here in the US, the products we're talking about are not PFAS. Now, if you look at, for example, the EcoReach dossier in Europe, under that definition, a lot of them are. Keep in mind, though, that the ECA dossier, that's a proposal.
Yep.
Okay, and we're currently in the consultation period, and they are looking for input from the industry, and they're going to get a lot of it. Okay, because what they're proposing, has a lot of implications. So they're going to get a lot of input, and that proposal may change significantly from where we're at now. The one thing I will say is, well, there's a couple things I'll say, is that however that shakes out, I think fluorine chemistry and F gases are going to be a big part of our future, because the bottom line is that for a number of applications, there really are no credible alternatives.
Appreciate that. Anyone else want to add anything?
I think what I'll say, Tristan, is it's certainly in our purview, in our environmental center and across the organization, right to the top of our company. And there's a few reasons for that. It's primarily driven by what is going on in Europe, and that they're the ones more aggressively pushing it. So what does that lead to? It leads to understanding what it is. And we don't necessarily know what should be a PFAS. So it comes down to the definition Stephen meant, and what shouldn't be a PFAS. And sometimes legislation or regulations get passed out of concerns that may or may not be merited, and we don't know that yet. So I would really love anyone who's an expert to really look at all the various fluorinated gases, their associated byproducts from atmospheric degradation, to decide which ones really should be a concern and not be a concern. That would be wonderful if we could use a science-based approach. It leads to, because of the movements in Europe, which we're tracking here, I'll use that example of, the monoblock outdoor unit that makes hot water. I said we have advanced R&D that's been public to use 454C as well as propane. Why both? Well, it's because you need parallel advanced R&D depending on where the regulations go and what customers want. So if the PFAS reg doesn't become something of concern in every European country, 454C is probably the better alternative because it meets their F-gas phase down requirement. It's a much lower GWP. If the PFAS is a concern, well, guess what? They're going to need propane, and the units are going to have to be kept, 20 feet away from the building, but that's possible. So it's certainly steering us. And when you look at the broadest definition of PFAS that even some US states have defined, there aren't a lot of F gases available for you to use if that really holds.
Yeah.
You're basically going to use R32, and maybe there's one other HFO that I've been told, and there might be more, but it doesn't give us a lot of choices. So it's definitely a developing situation.
Yeah. So that's perhaps a good segue into changing gears slightly from alternative refrigerants to leakage.
Can I add one?
Yeah, absolutely. Sorry, Jennifer, go ahead.
I just want to call attention to the fact that I agree with everything that Stephen and Philip just said about the definitions, and it's potentially problematic, but it's not just the fluorinated gases. And I know that's our focus today, but there's a lot of fluoropolymers and fluoroelastomers used throughout our systems that would also be caught up in that, and that likely don't have very good alternatives today in terms of reliability. So, we are all paying attention to this, and I agree 100%. I hope the science prevails, and that, where there are true environmental concerns, that we move to better alternatives, but that essentially we don't throw out everything just because we can classify it as a PFAS under a definition. So again, trying to provide the best science and data where we can, and hope that this comes out, in the best way possible.
Yeah, I appreciate that comment. I think science drive the decision making is really critical to all the conversations we're having in regards to refrigerants. Well, switching gears slightly and talking about reducing leakage, and I know we want to come on to refrigerant lifecycle management here, so I want to get some questions in, and then there was some specific questions in relation to the study that was referenced, Philip, in your presentation. So hopefully we can unpack those here in the next 5 to 6 minutes. I guess just starting off on refrigerant lifecycle management, some would argue that the type of refrigerant doesn't matter if it doesn't leak. We all know the reality is these systems leak. I think what we're struggling with as an industry, really globally for that matter, is that we really arguably don't have the documentation and reporting we need to really fully understand what lifetime leak rates actually look like from manufacturing through operation and of course capture, reclaim, or end of life leakage and or destruction. So Stephen, you mentioned onboard leak detection. I know that's a huge factor going forward, especially as it relates to A2Ls and slightly flammable refrigerants. But I guess, how are you all thinking about refrigerant lifecycle management? I know you're manufacturers, right? So once it's in the field, I know it's still important to you, but it may not be as critical as it is for some of the folks on the line that are either in the service industry or are working with the end users to make sure that they're thinking about the 20-year life cycle on this equipment and how it's going to operate over that life cycle. So I guess the pointed question is, are you thinking about refrigerant life cycle management? How are you thinking about it? And how can we ensure that, one, we start to capture better information in terms of life cycle leakage, but also how we try to cut the leakage off to begin with and avoid the fugitive emissions?
Okay, I guess I'll start. All right, so the first thing is, you're right, there's not a lot of good data out there, okay? But what our industry has shown us is they can really make big differences to drive leak rates down. I'll use green chill as an example, EPA's green chill program. I commonly hear average supermarket leak rates of 25% a year. Very skeptical of that number, okay? But EPA green chilled members have shown that they do have some significant leak rates, and they have shown that they can greatly reduce those leak rates. Now, I haven't followed green chill in a while, but they were down leak rates around 7%. And that's for a supermarket application with miles of piping and hundreds, if not thousands, of potential leak points. Okay. So we can, as an industry, get a lot better and drive our leak rates down. And I think, like we mentioned, the onboard leak detection that you're going to see in a lot of A2L systems is really going to help with that. Heard manufacturers who say are putting, field trials with systems out there, is they're finding small leak rates that they didn't find before. Okay, and that's key. That's big time, because if you find a leak shortly after the system's installed, when it's small, before it gets big down the road, that can make a huge input. And obviously, as a refrigerant manufacturer, I'll just wrap up because we got to give other people some time. We're obviously committed to circular economy, circularity, and recovery and reclaim of refrigerants, and is a big focus of ours going forward.
Can you speak to that really quickly? There's a question in regards to destruction and the impact of destruction at end of life, and how that compares to the fugitive emissions. And my answer was, destruction accounts, it reduces the impact by about 99.9%, if not, we could go into the decimal points there. But and I don't assume that any of you are experts on refrigerant destruction, perhaps, but if you want to add any points there.
For me specifically?
Sure. Yeah, you specifically.
Okay. All right. Reclaimers, a lot of times what's happening is they're destroying refrigerant. A lot of times it's contaminated refrigerant because they don't see it as having value. Okay. And if you have something that's badly contaminated, obviously that's an issue. But with the allocations going forward, these refrigerants, recovered refrigerant, has value, and it's important. And so I think there's an argument to be made for capturing that value and, reusing that refrigerant.
So want to sorry, go ahead.
I was just going to say, you asked if I'd say refrigerant life cycle management is a huge area of focus for the Daikin group globally. One of the links that was on one of my slides, you can go there and you'll find information on it. We haven't figured it all out yet. So there is a particular division in Europe looking at, can they create a circular economy around refrigerants? So we're watching how that works and what are the hurdles and what are the problems and can they manage that difference? But certainly I will say that one of the single largest opportunities is vastly and greatly increasing the amount of reused and or reclaimed refrigerants today. It's a huge opportunity. And unfortunately, for the longest time, the economics just don't prevail, and we're in a capitalist society, and it's very difficult to do. So that is something that we absolutely have to look at across the board with all stakeholders to figure it out.
Appreciate that. And Jennifer, maybe for you really quickly, how do you think subsection H of the AIM Act will influence this? And I know data sets, as we've all outlined, are lacking, given a lot of the data that we have right now is on the minority of systems out there, i.e. HCFC systems that are deployed in the market above 50 pounds. What are your thoughts on subsection H and how that will impact these data sets and the growing knowledge of refrigerant life cycle management?
So we expect that rule to be, published as a proposal in the September timeframe, maybe a little earlier. I think we heard this week that it was at OMB already, so we know that it's in process. Largely expect, similarities to Section 608, although the AIM Act also pulled in things around installation requirements and reclaim, which were not part of Section 608. So very hopeful that we see some developments there in terms of reclaim, and whether that's record keeping and reporting. We also saw some additional record keeping and reporting proposed under the technology transition rule. So we'll see what that looks like when it's published as final. But, unless there's good data, you could go out and survey technicians and contractors, right? And I think a very large percentage would say that they're recovering refrigerant today, but we're just not seeing it in the marketplace. And so I think the question is, from a policy perspective, how do you implement a program that's not too burdensome, but also has enough there to enforce, right? And so that's always the struggle. I mean, when we talked about this before, to your point, if refrigerant systems didn't leak, the refrigerant used in them would be a non-factor. But how would a regulatory body enforce that? And so that was always the complication there was, well, maybe we didn't need GWP limits. We could just reduce leaks to 0, but how do you enforce that? So it'll be an interesting balance. And I would just say that, regulatory compliance is going to drive a lot of this leak detection that we've talked about, but also sustainability goals. I mean, all of our companies have sustainability goals. Retailers have sustainability goals. Your customers largely are going to have sustainability goals. And so above and beyond minimum compliance, I think there's going to be a value in leak detection and minimizing those leaks, from your bottom line in terms of your emissions reporting even.
I appreciate that. I know we have one last question, and I want to actually turn it over to the group here that are on the line. And this question, it was kind of a combination of Brian, Jacob, Kim, and then others kind of put +1s on it. So Philip, it's specifically to you, but I think it opens up the question in regards to the type of data that's being used to calculate a lot of the overall impact, call it total equivalent warming impacts. As you referred to it, well, I forget your acronym, but the life cycle climate impact effectively. So the question around the reference study, and I'm sure there's others that have come out, and maybe we can collectively point to them. None come to mind, top of mind for me, but was, electricity was comparing carbon emissions from 2011. Obviously, the grid ratio in terms of emissions has changed over time. The other question that came up with that is, what were the assumed fugitive emissions rates or the leakage rate associated in that study? And just want everyone's perspective on, obviously the grid portfolio is constantly changing, but also, again, as we were just talking about, leakage rates associated with different applications more often than not are modeled. We don't have really good data. So for that study in particular, can you speak to that and maybe the need or any updated studies that have come out in regards to overall embodied / operational carbon associated with AC heat pump applications?
I think the only thing I can answer is in that study, it was a study of residential equipment. And what the university researchers did was they looked at all published data that was out there in terms of leak rates for ducted residential split systems, which includes the really high values, whether it was the EPA report, and there were other reports, and there was a whole data set. And then the university decided here is the right number to use. It was kind of a mid-range, and I don't remember what the number was. So it certainly wasn't 1%, but it certainly wasn't 25%, because they looked at that data and kind of went, boom, this is the right place to be. It makes the most sense. That's where it was in the study. Other than that, there have been definitely, you can Google lifecycle climate performance or LCAs and or TUIs and find what assumptions were used, because it all comes down to the assumptions. It's a really good question. I just don't happen to remember the number offhand, but it was something the university decided to go with because we couldn't dictate it to them.
Well, I know I know everyone on the call is thirsty for more information, more data, and I think part of the forum's intent is to start circulating more information on this subject matter. But really appreciate all the thoughtful answers to the questions. I know we didn't get to any and all of them, but I know there's more flowing in that I haven't been able to keep up here in the chat too. So I'm assuming this conversation will be continued at a later date. But again, really thank you all for your thoughtful answers, and Corey and the MEP 2040 team for hosting today. With that, Corey, I'll turn it back over to you.
Awesome. Thank you so much. And thanks for leading that conversation, Tristan. And I guess part of what we've been talking about said, if we can get leakage to zero, I think that if any of y'all have any data sets or better numbers that you could share with us, or ongoing research about what that leakage rate is, or what we should be using in our calculators and studies, that would be super helpful. Because like you said, it's not 15%, it's not 20%, but it's certainly more than one, and that changes that life cycle impact pretty significantly. So, all right, well, thank you all so much. Thank you for being here. Thank you, Tristan and Philip, Stephen, Jennifer, and Steve Kujak too, who had to leave early. Now we want to do sort of our working group updates, a little bit of MEP 2040 housekeeping here. I guess I can start as our DAR update. What we've worked on recently, obviously planning this panel in the session, but also putting together a companion piece to the open EPD letter to manufacturers. And so that we've done one that's refrigerant based, and to go out through Building Green, hopefully once it gets approved with the final edits from the steering committee to be published. Exactly what we were talking about today, that as an industry, I think what I heard from everyone here is that there's so much that has been regulatory based, and that it's all been regulations driving the manufacturers to make these changes. And I think that as an industry, we really want it to be not regulatory based, but that we want it to be demand based, that as an industry, these are the things that we're asking for, and that creating a demand and a change faster than what is just required simply from regulatory conditions there. And I think we need to figure out what are those movers that we need to be able to provide to the manufacturers to make that happen. And so I think this open letter is part of that, and making that known in the industry. So that's been major update that we're working on, hopefully to be approved and be published very soon. Do we have anyone from the communications and or EPD group that would like to provide an update? I don't know who we have still left on the line.
Andrew Himes should be able to provide an update.
Andrew, are you there? I don't know. Andrew may have stepped away.
Or Rob Bullen, if you're available. All right.
Maybe
Let's move
not.
to the next group.
Let's see, what is it? Is Christy on? I know she was on earlier. She could speak for the EPD group, right? No, a lot of folks started to drop off there as we were getting closer to the end.
Mhm.
So we may have lost a bunch of them. So I guess, is there any other updates we need to make, Kaylee?
No, I don't think there are any to the general group. Did you give the update on the one click?
No, I didn't.
So we are approaching a conversation with One Click right now, which is an LCA software that in my experience is predominantly used in Europe. But to have an MEP specific application for this group that would be available. So we're really looking forward to collaborating with them because the embodied carbon space for MEP is so difficult with the lack of EPDs. So I think just having a partner to collaborate with and having a user interface that's really clean and clear and readily used elsewhere in the industry is an ideal partnership. So yeah, look out for updates on that.
Great. All right. Well, if there's no other updates, then maybe we're done just a few minutes early. Once again, thank you for everyone for being here. Thank you for our presenters and Tristan for leading the conversation. And once again, if there's anybody that wants further information, you can find it on our website. If you want to become involved, you can reach out to any of the steering committee members, or myself. And of course, for anybody that missed this recording and slides will be available on the MEP 2040 website later on. So thank you so much, and everyone have a great rest of the week.
Thanks, everyone.
Thank you.
Thanks, everyone.